Hello, my name is Paul Craig. I'm a professor of biochemistry at the Rochester Institute of Technology in Rochester, New York, USA. And I'm pleased and honored to be invited to give a talk at the IUBMB, FAOBMB College of Biochemists of Sri Lanka Virtual Education Symposium this year. And today I'm going to share my screen now. And today I'm going to be talking with you about Python scripting for biochemistry and molecular biology in Jupyter Notebooks. And this is about a workshop I've developed. I spent the spring of this year on a professional leave with Jessica Nash and T. Daniel Crawford at the Molecular Sciences Software Institute and working with them there at Virginia Tech. And I'm going to be talking about the workshop I developed. So a bit of an overview of the talk. I'm going to talk about data analysis and teaching biochemistry, about what is a Jupyter Notebook, particularly about the data analysis limitations of Excel. I'm going to talk about creating the Jupyter Notebooks and the workshop that's built on them. I'll do a live demo of several workshop lessons. And finally, I'll talk about some future plans and resources. So when I think about data analysis in the teaching lab, right now I'm involved with a project called BASIL, which stands for Biochemistry Authentic Scientific Inquiry Labs. And in these labs, we do a lot of experiments actually, but two of the experiments are protein concentration and enzyme kinetics. And so we try to plot our data in Excel and it works reasonably well, but I'd like something better. And I also have a desire to teach more deeply. I don't want to just have students plotting a straight line in Excel and predicting protein functions or protein concentrations from there. I'd like them to be able to see confidence intervals and understand the meaningful or the more reliable parts of a calibration curve. I'd also like to be able to demonstrate nonlinear curve fitting, which can be done in Excel, but it's difficult. And a couple of years ago, a colleague of mine was demonstrating some things he'd learned at a workshop on Jupyter Notebooks. And he showed me about simulating enzyme kinetics in Jupyter Notebook. And I was very excited at that point and completely hooked. So what is a Jupyter Notebook? So a Jupyter Notebook is an online resource. So you have to launch the notebook in a browser. And within that notebook, there are cells. You can do calculations in those cells. You can write text in those cells. So it really is a notebook in the same way we use a scientific notebook, where you would write text and commentary. You go through and do calculations. But the power of this is that the calculations are done by Python. And so you can do some pretty remarkable things. Basically, anything Python can do, you can do in a Jupyter Notebook. So why go to Python scripting in Jupyter Notebooks? I mentioned before my frustrations with working with Excel, and the computational power available in a Jupyter Notebook using Python 3 far exceeds what you can do with Excel. It's very flexible and customizable, so you can design your own experiments, you can design your own notebooks. There are remarkable resources available. So a lot of what I do isn't just creating things from scratch, but searching the internet to see who has done other things, who has created materials that I can use, that I can borrow. And this is all part of an open source community. So people in the community are creating resources all the time and sharing them. And these are freely available. It's very exciting. So you might be thinking, well, I'd really like to try using something more advanced computationally in my teaching, in my labs and my courses. But well, I'm pretty comfortable with what I use right now. I do most of my work with maybe Excel or maybe with Google Sheets or something like that, and it works reasonably well, and it does. You might not have any experience with coding, and so you might be bashful about trying to do some coding. Maybe there are institutional structures. Maybe your institute doesn't support computers that could work with this, or they wouldn't be willing to have you introduce some of the tools you need onto their computer system and their firewall. There are also maybe textbook standards. Maybe the books you use, the textbooks you use computational resources. And there's no room in their curriculum, at least the way it's seen by the publishers, for Jupyter Notebooks. Or maybe you're in multi-section courses and maybe you want to make a change, but the other faculty involved don't want to make a change. And so that can be a real challenge to try to win people over. to this, or to do something unique in one section versus other sections. The students, where I'm from, the students often resist that if they think they're having to do more work than the other sections are. So those are some of the barriers. But I'm going to talk about creating the notebooks, and I want to convince you that it's not that difficult. You can learn how to do this. And the subjects for the notebooks, some of them are actually borrowed directly from the Python Scripting for Computational Molecular Sciences workshop that Ashley Ringham McDonald developed for MOLSI. MOLSI is the Molecular Sciences Software Institute. Also, I interviewed a bunch of colleagues. I was actually talking to my wife and saying, well, what should I put in these notebooks? And she said, why don't you ask your friends? So I did. And so I asked them what experience they had with computing and coding. I asked them what they would like to be able to use computers to do in the lab that they can't do right now, either for their teaching or for their research. And so they come up with a bunch of subjects. The idea of just being able to convert raw data into derivatized data, maybe automatically build a standard curve just by importing the data, for example, or being able to predict the amount of enzyme you need for an assay, and actually set up the notebook to do that for you, so you don't have to keep putting things in cells and entering formulas. Maybe predicting pH profiles for enzymes with amino acid substitutions in the active site. And finally, looking at equilibrium calculations that are dynamic, so you can change different features in the calculation and see what effect that's going to have on an equilibrium process. That could apply to acid-base chemistries, solubility products, all kinds of things. And so those are just a few ideas that came in. And so I developed the notebooks. I'll talk about the notebooks in a minute, but first I want to mention about the workshop itself. The workshop involves 4 3-hour sessions, and I spaced them out a little bit. It's a lot of information to learn at one time. And usually the workshops include some kind of a homework that you need to take home and work on. And so, there's only so much any student can absorb in a given setting. And so in this particular case, we have 4 3-hour sessions. This is a live coding process. So you don't just watch me demonstrate what to do with the code. I actually put up empty notebooks and build the code along with you. So it's live coding. We go through the code one line at a time. The focus here is on practice and not on theory. And as I said, there are exercises in the middle of a notebook. I try to put 3 or 4 exercises at least in the 3-hour period, so you can kind of do a check-in to see, did you really get it? Did you understand what it means to be able to do this kind of printing or to do this kind of plotting, for example? And also there are homework assignments that go with it. Now, the workshop is based on 8 different modules. There's an introduction, and we'll actually take a look at that today. There's a file parsing module where you learn how to pull data out of files extracted from the protein data bank. There's also a module on processing multiple files and writing files. So you actually pull information out of multiple files from the protein data bank and then write to a separate file. We talk about working with pandas. Pandas is a wonderful library in Python for data analysis. We look at linear regression, and so that's using something called the SciPy library to do statistical analysis. Also look at creating plots in Jupyter Notebooks. And finally, the last 2 are on nonlinear regression with Michaelis-Menten kinetics. So to do these workshops, I needed to have people participate. And so my recruiting process started with teaching science with big data. And so this was a workshop or a conference that was sponsored earlier this summer by the IUBMB and the ASBMB, that's the American Society for Biochemistry and Molecular Biology. And so that workshop happened in June, and I gave a presentation there and invited people to come. And so many of the people came from that presentation or from that workshop. I also emailed contacts to my colleagues in the Basel project to see if any of them were interested. And I contacted friends who expressed an interest or just names that have been given to me. You might want to check with so-and-so. And so I did that. And so as a result, we set up the workshop. And the logistics were that the workshop was scheduled from 2 to 5 p.m. That was Eastern Standard Time, so that people on the West Coast of the United States could participate. And it would be morning for them. So this was actually scheduled in the afternoon on a Wednesday, Friday, Monday, and a Wednesday. So that way, participants could attend the workshop for 3 hours. and then hopefully find an hour or two between that time and the next workshop to go through the homeworks and maybe review some of the concepts. And the hosting we did in Zoom. Jessica Nash from the Molecular Sciences Software Institute and Ashley Ringer McDonald, who is a MOLSI associate, were co-hosts. And we used Zoom because it gave us stable connections that worked almost all of the time. And also, before starting the workshop, I sent out instructions to participants about how to install something called Anaconda that I'll talk about in a minute, and how to create a GitHub account. And these instructions, I also created a video to show them how to do this, to walk them through it. And I met with a few folks and actually hosted a session where they could do that before the workshop started. So Jupyter Notebooks, as I said, they launch in your web browser. But in order to do that, you have to install something called Anaconda Navigator. And I'm not sure how clearly you can see this on your screen. But once you've installed Anaconda Navigator, and it installs on Windows, on Macintosh, or on Linux, once you've installed it, then you can go in and click on the launch button here under Jupyter Notebooks, and it will launch a Jupyter Notebook for you. And we have an online Jupyter book that will be linked to this presentation. You can actually go in there and see the material and information for the workshop and read through it. And you'll notice here that I have the different modules that I talked about on the left-hand side, and plus a setup pane where you go in and it teaches you how to set up Anaconda. It also has a setup where you can download the data for the workshop and a copy of the workshop schedule. And also notice for each of the workshops, we have a question. What's the main question we're going to address in this workshop? In the introduction, the question is, what is the basic syntax of the Python programming language? And we have some objectives. So our objectives for this first workshop were to assign values to variables, to use the print function to check how the code is working, to use multiple assignment to assign several variables at once, and then finally to use a for loop. And a for loop is a tool in Python you can use to perform the same action or calculation repeatedly on items in a list. And so this is what the online Jupyter book looks like. And before actually going there, I want to talk a little bit about my approach to teaching. So once again, this is live coding exercise where I start off with an empty notebook, just like everybody else, and I teach the workshop participants how to write code in the notebook, also how to write text in a format called Markdown in the notebook. So it's live coding. And the process I use for each workshop, and in fact, for each step in the workshop, is what I call what, why, how. So I tell first what. Okay, this is what we're going to try to do. These are the questions we're going to try to answer. The why is, well, why would I want to do that? What would I gain from doing that? And finally, the how is the details. Here's the code you have to write to get this to work. Here are the data you have to upload. Here are the data structures you have to build, things like that. So in these teaching sessions in the workshop, the host leads the session. Okay, so the host will take you through one at a time. But then we have co-hosts. And I mentioned a couple that helped me in the workshop that I ran recently. And these co-hosts help people when challenges come up. And also in the process of doing the workshop, we have regular checks for progress. And so recently Zoom added some buttons that you could check to indicate, to raise a hand, ask a question. But quite often I'll go through a piece of code and ask people, did it work for you or not? Were you able to get it to work? And they can put in a green check mark to indicate that it did work, or a red X to indicate that it didn't work. And so they communicate that way. And then the co-hosts look for the green check marks, and particularly for the red X's, to tell them that they need to go help these people. And so, by the way, I should mention this workshop was entirely online. All right, so now I'm going to do a brief live demonstration of a few of the notebooks. We're going to be looking at some calculations in Jupyter Notebooks. We're going to look at plotting the data, and also look at nonlinear regression of Michaelis-Menten kinetic data. And so I'm actually going to switch what I'm displaying on the screen. And this could take a minute. And now I'm going to share. All right, so this is actually the Jupyter book that I mentioned. So it's live, and there's information here on installing Python and so forth. But we're going to move now to the introduction. All right. And I just want to point out a few things. Once again, we have always questions and objectives, so learning objectives for a process. And I'm going to scroll through here, but I just want to show you a few tricks. So in these cells, we can actually go through and do calculations. So if you put in 3 plus 7 in a Python 3 coding cell and just hit Shift Enter, then it gives you the calculation. It calculates the value is 10. Well, that's not very exciting, but you can do things that are much more exciting than this. For example, here's a simple problem where I've assigned a Km value of 15.0, a Vmax of 100.0, a substrate concentration of X, and solving for the velocity when we have that Vmax, that Km, and that substrate concentration using this equation. So when I do that, I go through and it solved the equation. However, notice it didn't print an answer. That's because I didn't tell it to print. So in the next cell, I just say print velocity, and it gives the value. And I'm going to skim through to a couple other things. Another thing we can do in these cells is we can actually assign 3 variables at once. In a single equation, so I assign Km, Vmax, and substrate concentration all in one line. And when I do that, I get the same result. Now it's possible in Python to create lists. And so here's a list of substrate concentrations. You could make, you could do these one at a time. But in fact, what we do here is we take that list of substrate concentrations and we go through and we calculate the velocity for each of those concentrations. And so this is what's called a for loop. I mentioned before that for loops are used for running repeated calculations. So when I do the calculations, I get the velocities at each of these substrate concentrations. And so this can be very useful. And so this is a standard approach when doing these types of notebooks, is that you can do repeated calculations with a single set of commands. Very convenient. So that's just a little bit of introduction. Now I want to look at creating plots. And so when we look at creating plots, the question is, how can I plot and annotate my data in Jupyter Notebooks? And the objectives here are to repeat a linear regression that was actually done on protein assay data in a previous module. And that's done to obtain best fit statistics. And then we create a plot for the best fit line. And finally, we're going to create a plot that includes confidence intervals, which really excites me. So when we work in Jupyter Notebooks, the Jupyter Notebooks don't contain all of the tools that we need. So sometimes we have to import other libraries that contain a lot of other functions. So in this particular case, we import the OS library, the pandas library, and the SciPy library. And once we do that, we can take some data, which is imported here. It's just some protein assay data, so a calibration curve for a protein assay. And you import the data, and then you run it through the calculation using a function called linregress from SciPy stats. I realize I'm saying a lot in a hurry here, but these are just some things we do in the workshop. And you can do those calculations, and once you do those calculations, you get a bunch of results. And so this particular calculation gives us the slope, the intercept, the R-squared value, the p-value, and the standard error for this particular protein assay. Well, the numbers are useful, but it's more helpful if you can plot the data. And so I'm going to go here and actually do a plot of the data. And you can see in this plot that we have, here's our y-axis, which is the absorbance, and our x-axis, which is protein. But it's not annotated. There's no best fit line. So we then go and add a best fit line and some annotation. And I'm not going to go through all of those details, but I'll show you the final result. So here we have a plot where we have the absorbance versus the protein, the amount of protein. We have the best fit line, and we have the equation for the best fit line. And so it's very easy to produce these in Jupyter Notebooks. And in fact, it's also possible, there's a command here called save fig. It's actually possible to save publication quality graphics from a Jupyter notebook and then put them in a paper you're going to produce or post them on a website. So, but I wanted to go further than this. I wanted to show confidence intervals. And I started looking at using this particular library called matplotlib to do that. And a friend of mine told me about another library in Python called Seaborn. So I went into Seaborn, and in about 20 minutes, I was able to run the same exercise, only in this case, I do a best fit line with the data, but it also includes the confidence intervals. And you can see that the data are more reliable in the middle of the curve here than they are at either end. And so just a very nice feature that you can do with this Creating Plots notebook. And finally, I'm going to take a look at nonlinear regression. And once again, we start off with a question: how can I perform statistically robust nonlinear regression in a Jupyter notebook? And so the objectives here are to import our data again from something called a CSV file. CSV files are comma separated value files. Actually, Excel can open those. You learn how to create a function based on an equation that we're going to fit, and that equation is the Michaelis-Menten equation. We then use tools in Python to generate a best fit curve with parameters and then create plots of the data. So we'll go through this one step at a time. So once again, we have to import libraries of the functions that we need. And I won't go through all of these. And here is the Michaelis-Menten equation, which is probably quite familiar to you. And what we're going to do is we're going to create a version of the Michaelis-Menten equation in our code and use that. And so initially, I'm importing the data into something called a pandas data frame. And when I do this, you can see that I have the concentration of the substrate. In this case, it's paranitrophenyl phosphate, the slopes of the initial rate curves, and then the initial velocities once we adjust for the extinction coefficient for the product, which is paranitrophenol. And following that, we're going to plot the data. So this is a very simple plot of the data, and the y-axis is the initial velocity, and the x-axis is the substrate concentration. And you notice we have the curve, the rectangular hyperbola curve we normally see for Michaelis-Menten plots if the enzyme follows Michaelis-Menten plots. And so we have those data, but now we want to fit a curve to those data. And in order to do that, we create the Michaelis-Menten function. I call it MM here, and calculate the rates. And so this is the rate that the Michaelis-Menten function will perform for the substrate concentrations we have. If the Km is 100, the Vmax is 100 and the Km is 1. And so I need to assign, that's an error, but I don't have time to go through the error. I forgot that I introduced an error there. Here's a curve fit function. So this is a function that's available in something called the SciPy optimized library that will actually fit the data that you generate. So what we have to give the curve fit function, we have to give it the function we're going to fit to. In our case, it's the Michaelis-Menten function, and then the x data and the y data we're going to use for fitting. And when it does that, it's going to give us two parameters. And those two parameters we can use then to derive the Km and Vmax. And so this is the line that actually does the curve fit. It's a very simple calculation, it's very rapid. But now we have information that's stored in these variables that we want to extract. And so we need to extract the Km and the Vmax from the P-opt is the optimized parameters, and P-cov is a diagonal matrix of the errors of those parameters. And so going through this calculation, we get Vmax and Km values for this reaction. And there are better ways to display this. If we don't want to show it with, let's say, 14 decimal places, we can tell Python exactly how we want to print it. But it's even more interesting to plot the data. So if we take our data and we plot the data, once again, this is the initial velocity, this is the substrate concentration, but you'll notice in this plot that we have the lines become a bit, they're just straight lines from point to point of the predicted value. So the line's a little bit herky-jerky. Well, it's actually possible to go in Python in a Jupyter notebook and actually do a smooth curve of that fit. And that's explained in the notebook. And when we do that, we get this lovely smooth curve. The smooth curve is shown in red and the data points are shown in blue. So those are a few things that we do in the notebook in the workshop. And now I'm going to switch back to my PowerPoint presentation. And so we went through those notebooks. Just want to mention a couple of other things. My future plans are to host live workshops and also to create a recorded workshop on YouTube with all the online resources that are necessary to run that. And also am very interested in developing more modules for biochemistry and molecular biology education. And if any of these things interest you, you can contact me at paul.craig@rit.edu. And finally, I just wanted to mention a few resources. So the Python scripting biochemistry at the GitHub Mostly Education site, the link is here. And I'm going to provide a PDF of this presentation so that you can download it, and it'll be provided through the meeting. Also, the Jupyter book of the workshop is at this link. And then finally, the link for the Molecular Sciences Software Institute is here. And that marks the end of my presentation. Thank you very much.